All right, hi everyone. Just wanted to go ahead and make a video for you all. So I'm just gonna kind of recap um, the sections we covered this week, and hopefully add just a little bit more where I saw that the text may have been lacking. So we're gonna start with one-to-one functions. So one of the ways that we will determine whether or not a function is one-to-one when we're looking for that function's inverse is if we assume that f of x1 equals f of x2, and we get, and we get that x1 equals x2, then f is one-to-one. And the fancy word that mathematicians have for that is injective. More commonly, you're going to see one-to-one though. So let's run through an example of that. So let's say f of x is 3 minus 1 over x, okay? So assume that f of x1 equals f of x2. So we have that 3 minus 1 over x1 equals 3 minus 1 over x2. Now we want to use algebra. We want to just manipulate this equation and eventually get to what we want is x1 equals x2. So if we subtract 3 from both sides, we can just cancel that off. And then since both of these are negative, we can multiply both sides by -1. So we don't have to worry about that being negative. So we have 1 over x1 equals 1 over x2, which tells us that x2 over x1 equals 1, which in turn gives us that x2 equals x1, which is what we wanted. So we can now conclude that f is 1-to-1. And then we can go ahead and look for an inverse of that function. Okay? Now, there's an alternative way to do this using calculus, and it really depends which method you may want to use. Sometimes the calculus is easier. Sometimes the algebraic approach is easier. So let's go ahead and use the same function. So f of x is 3 minus 1 over x. Okay, so f is 1-to-1 if we have that f prime is greater than 0 on a given domain, or f prime is less than 0. And you can think about this graphically. So just imagine we have a little xy axis here, right? If a function is if a function's first derivative is either always positive or always negative, that means that that function's increasing, which means as we scan left to right, for example, it's just going to be climbing if the derivative is positive, or it's just going to be decreasing if the derivative is negative. But the point is that there's if a function satisfies these conditions, either one of these conditions, it's going to pass our horizontal line test, which is the easiest way to check for if the function is 1-to-1 or not. So let's go ahead and evaluate that derivative. So I'm going to put this in a calculus-friendly form. F of x is 3 minus x to the -1. So f prime of x is the derivative of 3 is 0. So that's minus 1, x to the -2 is x to the -2 is 1 over x squared, right? So for x non-zero, we have that 1 over x squared is greater than 0. So we can conclude that, therefore, the function f is injective or one-to-one, if you prefer. Okay. So I just wanted to circle back to the algebraic method. If we assume that f of x1 equals f of x2, graphically what we're doing is we're saying, okay, well, let's assume that we have some situation like this. F of x1 equals f of x2 means that there's two x values for that given y value. But if those two x values happen to be the same, i.e. x1 equals x2, well, then it passes the horizontal line test, because that's basically what this is just saying is, okay, well, if we put a horizontal line through at that specific y value, we actually only intersect the graph once. If we assume that we intersect it multiple times, well, it turns out that we don't, and it's actually just the same x value. So don't think about that too hard if that's tripping you up, but I just thought I would add that because I didn't see that covered in the text very well. Okay. So let's try finding the derivative of an inverse function at a specified point. So let's start with the function f of x is tangent of x. Okay. So there's a neat little formula that's actually pretty difficult to prove, but there's a neat little formula that just packages this up nicely. It says that the derivative of the inverse function at a point y naught, or at a value y naught, excuse me, is equal to 1 over f prime of f inverse of y naught. Okay, and this is the inverse function theorem. So let's take the point 1, I'll put a little divider, 1 comma pi over 4, and we'll say that that's equal to y naught x naught. The biggest problem that Calc 2 students typically have with problems like this is trying to determine, is this point on the f that was given, or is it on that f inverse I'm looking for? There's a little bit of subtlety there. But I'm hoping that if we think about this in terms of the inverse function, right? Because we would feed tangent pi over 4 and get 1 out of it. So this point is on the inverse function, and that's kind of why we use the y naught x naught. So that would be like taking the point x naught y naught on f of x, and then, well, when we reverse the order, that gives us the point on the inverse function. Okay, so to do this, we're going to need f prime, right? So f prime of x is secant squared of x. And I don't like working with secant so much, so if we'll remember from our trig, this is the same thing as 1 over cosine squared of x, right? Okay, second thing we're going to need, we need f inverse of y naught. Well, this is f inverse of 1, and it should be, the way we construct this, we don't need to actually find the inverse function and evaluate this, but this just ends up being pi over 4, right? So we're ready to put the pieces together. So f inverse prime at y naught, which is 1, is 1 over f prime is secant squared, or 1 over cosine squared. So this is 1 over cosine squared of pi over 4. And we'll just simplify that. When we divide a fraction, we divide by a fraction, we can flip and multiply, right? So that ends up being cosine squared of pi over 4. excuse me, cosine squared of pi over 4, which in turn is cosine of pi over 4 quantity squared, which is root 2 over 2 squared is 2 over 4 is 1/2. All right. So just to recap, we have that f inverse prime of 1, and I know this notation isn't great, but we don't really have anything better. The mixing the inverse and the prime is it's a little unfortunate, but we'll make it work. So we're ready to box that up. Okay. So I just wanted to kind of recap some algebra, solve some equations here. E to the minus 2x equals 6. We want to find x. So we can take the log of both sides. Log of e to the minus 2x is log of 6. Now there's kind of two ways you can think about this left-hand side. You can think of them as inverse functions. So when they cancel out, it's what was in the argument. Or we can use our properties of logs from algebra, and we can slide the power down in front. Minus 2x ln of e is ln of 6, and ln of e is known to be 1, so that's just minus 2x is ln of 6, and then x is minus ln of 6 over 2. And if we want to go through, we can verify if we plug this back in for x, we have e to the minus 2 minus ln of 6 over 2. The 2's cancel out, the negatives cancel out, and we're left with e to the ln of 6, which is 6. So that checks out nicely. All right. So second one I wanted to go over is, well, what if we have ln of x is equal to -1? So just like we took the log last time, we're gonna exponentiate both sides. So we have e to the ln of x is e to the minus 1, and again, when we raise e to the ln of x, those operations, they just cancel out. So we're just gonna get an x on the left-hand side. And e to the minus 1 is just 1 over e. So we have that nice little form. If we want to verify, we can actually use this just because it's a little bit easier. So ln of e to the minus 1 is minus 1 ln of e, which is just minus 1. So always good to double check your algebra when you can. It's a good habit to get into. I'm aware that it takes a little while, but if there's if there's ever any uncertainties, we have the power to check ourselves, which is really nice. So I just wanted to dip into some calculus now. So let's suppose we want to find the derivative of ln of 7x. Okay. So the way I think about doing these derivatives is whatever's in the argument, whatever we're taking the log of, we're just going to put that in the denominator. So automatically, this is just 1 over 7x. And then we need to multiply by the derivative with respect to x of that argument. And ddx of 7x is just 7. So we have 1 over 7x times 7. The 7's cancel, and we have 1 over x. Okay. Now, there's another way we can do this, though, because it's good to think about things in multiple ways. We can actually use the properties of logs to split this up as ln of 7 plus ln of x. Right? The log of a product is the sum of the logs. Oh, that's one too many. Well, the derivative is a linear operator, which means that it distributes over sums like this. So the derivative of log of 7 that's just a constant. That goes away. That's 0. And we're left with d dx of ln over x, which, if you'll recall from the text, is 1 over x. So if you thought it was kind of odd that there was this cancellation here with the 7s, this kind of gives a little bit of reason why that works. Okay. Let's say we want to do, or find the derivative of the log of x. Okay. We're in a place now where chain rule is always active. You know, in Calc 1, for a decent amount of time, you didn't actually have the chain rule to work with, but that's no longer optional. Everything we do, there's chain rule. Chain rule is baked into every derivative you take. You just don't see it for a good amount of these times. So the argument is ln of x. So again, when I'm thinking about these, I say, okay, well, we're going to do 1 over the argument times the derivative of the argument, right? So this is 1 over ln of x times d dx ln of x. And we know what this is. It's just 1 over x. So we have 1 over ln of x times 1 over x, which is 1 over x ln of x. Okay. Next thing I wanted to do is I wanted to give you an example of finding the equation of tangent lines, because we probably haven't done that since Calc 1. So it's always just good to have a little refresher, a little bit of algebra work here. So find the equation of the tangent line to f of x is e to the x divided by 2 minus x at the point 0, 1/2. Okay, so to find the equation of the tangent line, we need 2 ingredients. We need a slope and a point, right? And the slope comes from the derivative, and we are given the point. So all we need right now is the slope. F prime of x is, when we differentiate e to the x, it's just e to the x. So I'll be a little more explicit here. E to the x over 2 minus d dx of x, because again, the derivative is a linear operator. It distributes over sums and differences. So this ends up being, and so recall from Calc 1 that we can slide constants out in front of the derivative. So this is 1/2 d dx of e to the x minus, and I'll just go ahead and say d dx of x is just 1, and then d dx of e to the x is 1/2. So f prime of x is 1/2 e to the x minus 1. Okay, so we need the slope of this line at the point x equals 0. So we can go ahead and evaluate that now. F prime of 0 is 1/2 e to the 0 minus 1. Anything to the 0th power is 1. So that's 1/2 minus 1 is minus 1/2. Okay. So now we're ready to use, I prefer to use point slope form, but you can use slope intercept form as well. But the form I like to use is y minus y naught is equal to m times x minus x naught, where x naught, y naught, x naught, y naught is 0, 1/2. So we have y minus 1/2 is, and I'll say this is m, is minus 1/2 x minus 0. So we have y minus 1/2 is minus 1/2 x and y is minus 1/2 x plus 1/2. And that's the equation of our tangent line to f of x at the point 0, comma 1/2. Okay. Next thing, let's do some indefinite integrals. So we're going to be evaluating. We want to evaluate e to the sine of x over secant of x dx. Again, I don't really like to work with secant if I can avoid it. I think putting things in terms of sines and cosines for me generally makes more sense. So I'm going to go ahead and rewrite this as e to the sine of x dx over 1 over cosine of x, because 1 over cosine of x is secant, right? So again, we can flip and multiply, which this simplifies to e to the sine of x times cosine of x dx. Now this is starting to look suspiciously like a u-sub problem, right? Because we have kind of a complicated function. We have a rule for integrating e to the x. We don't have a rule for integrating e to a function of x generally. So suspiciously like a u-sub, because whatever's in the argument there, we also conveniently have the derivative of it here. So we'll say let u equal sine of x. So du is cosine of x dx. So all of this can now become e to the u, and then this whole piece just becomes du. Now this looks like something that we know, and we know the rule for. So this is just e to the u plus c1. And now, don't get wrapped up in this, but technically we need a different constant for the u integral. But when we come back to the land of x's, we have e to the sine x. That's when we can change the constant. Don't worry about it too much. I'm not going to take off points for not having the correct constants, but it is worth mentioning. Okay. Next. So suppose y is 10 to the natural log of 2x. And we want to find dy dx. Okay. So we're going to need to apply logarithmic differentiation here, right? So first we're going to take the log of both sides. Okay, and we're going to use the properties of logs to go ahead and slide this power down in front. So we have that log of y is log of 2x times log of 10, right? Now we can differentiate. So the left-hand side is just y prime over y. And I want to be just a little careful here. So I'm going to take this in another step. Okay, log of 10 is just a constant, which means that it can slide out in front of the derivative here. So we have y prime over y is log of 10 times, now we're ready to differentiate the log of 2x. But again, that's 1 over 2x times the derivative of 2x with respect to x is 2, and we get a cancellation. So we have that y prime over y is log of 10 over x. Now, all that's left to do is multiply by y. So y prime is log of 10 divided by x times y. But we already had a convenient formula in terms of x for what y was. So we'll just go ahead and substitute that back. And y prime is ln of 10 over x times 10 to the ln of 2x. Okay, and just because the notation, we asked for dy dx, not y prime, so we can just go ahead and, because y prime just means dy dx, but since they asked for dy dx, we're going to put it here. So we'll box that up and we'll be ready to go. Okay. All right. So the last thing I wanted to address was, okay, now we need to start looking at derivatives of the inverse trig functions. And these are things that you're gonna have to memorize. The trig is gonna make a big comeback in this class. So if you don't have your unit circle memorized, now's a good time to do that before we start having the exams. You need to be able to evaluate inverse trig functions. Highly recommend looking under, I believe it's course materials for my class. I have recitation worksheets. Yeah, recitation worksheets under course materials. Go up to exam 1, and it'll have a nice little, it'll have a calc 1 review, inverse functions, exponentials, and inverse trig functions, derivatives of inverse trig functions. I'm not sure if we'll get to L'Hopital's before the exam, but highly recommend trying to work out some of those recitation problems. They'll be more on par with the difficulty that you'll see on the exams. So, okay. Let's just go ahead and dive into this one here. So we want to find d dx of sine inverse of x. No, sorry, excuse me. Not of x. We want something a little more complicated, e to the minus 2x. Okay, and again, when you're looking at something like this, you should automatically be thinking, okay, I have a composition of functions. I'm composing the inverse sine function with the exponential function. Gonna need chain rule, right? So I'm just gonna write this down because it's just to have for reference. But the derivative of the inverse sine of x is 1 over square root 1 minus x squared. Okay. So in this particular problem, x is e to the minus 2x. It's taking the place, right? So we pull this down here, d dx sine inverse of e to the minus 2x is 1 over square root 1 minus, and I'm going to put parentheses here, e to the minus 2x quantity squared times, and this is chain rule kicking in, d dx of e to the minus 2x. Okay? So we can go ahead and simplify this exponent. When we raise a power to another power, we can multiply. So we have 1 over 1 minus e to the minus 4x times, and again, we're seeing that chain rule actually gets implemented when we evaluate this derivative, but when you do enough of these, you can start to skip ahead and know the step of the chain rule. So this is going to be e to the minus 2x times minus 2, and then we just do a little bit of simplification here. And we have minus 2e to the minus 2x over 1 minus e to the minus 4x. So d dx of sine inverse of e to the minus 2x is minus 2e to the minus 2x over root 1 minus e and minus 4x. Box that up, and we're done. So that's kind of the broad strokes review I wanted to cover. I wanted to keep this video kind of on the short side just in case I had technological issues with it. I didn't want to be porting around this monster file. So this is kind of a test run. We'll see if this format is going to work. Like I said, I'm going to put this up on YouTube. So let's see. All right. Thank you all.